Okay, here we go. So more physics, a little bit more physics. We saw a bunch of physics applications last time, center of mass, for example. Moment of inertia is another physics thing. But this is not a physics class, right? So that's not the point here. The point here is that this is another really great application showing how you can use Riemann sums to compute something interesting, right? So anyway, moment of inertia is that thing. Now, I want to remind you of a fact that hopefully you all know from high school physics. This 1/2 mv squared. Does everybody remember that formula from high school physics? If you don't worry about it. Here it is. It's this thing called kinetic energy. And if you have a moving mass, however much that mass is, right, whatever velocity it's moving with, plug into this formula, and out comes this thing called kinetic energy, which has lots of important properties that would be heavily discussed in a physics class, which this is not, so we won't. Okay, but anyway, that's what it is. So this involves mass where every part of the mass is moving with a given velocity. And if you're moving in a straight line, like you're driving down the street in a car, every part of the car is moving the same speed. Right? That's really important. Otherwise the car gets torn apart. Right? So here's the weird thing. If you have a mass that's rotating, so let's suppose your mass is a great big lump like this, and it's rotating around this axis, you know, like a planet around the sun or something like that, right? Not every piece of mass is moving with the same velocity. This little piece of mass right here, in one period of the rotation, it only moves that far, whereas this little piece of mass over here, it moves a much greater distance in the same amount of time. It's moving faster, right? So here we have this situation again. We would like to just plug in to a simple formula and say, look, mass, velocity, plug in, do it, simple result. But something's not constant, right? And this is the constant problem. That's an unfortunate play of words. This is the perennial problem, right, that causes us to have to break things up into Riemann sums. Why can't we just multiply area times height to get volume? Well, because the height might not be constant, right? Why can't I multiply density times volume to get total mass? Well, the density might not be constant. So here, velocity is not constant. Okay, so the idea is we're going to break this up into pieces. By the way, a little bit of flashback to geometry. I hope you all might remember this. This is something called angular velocity. Angular velocity says instead of distance per unit time, it's angle per unit time. Right? And given that, if you know like how many radians of angle per unit time as something's rotating around, if you multiply by the radius, its distance from the axis, then that gives you the actual velocity. This is just a geometry thing. If you're not 100% comfortable with that, come to my office hours. I'll be happy to discuss at length. It's no big deal. Okay, so this is not a constant. It depends on where you are. And again, this is ultimately the problem, why we need an integral. Okay. But this is a constant. Right? Omega is a constant. So what we're going to do is we're going to take the formula for kinetic energy and we're going to rewrite everything in terms of omega and then have something a little bit easier to work with. So here's the big idea. Take some little piece of mass. Let me go back to a little piece of mass right there. Right? How much kinetic energy does that little piece of mass have? If I add that up over the entire solid, add up all those little pieces of energy, that's going to give you the total kinetic energy. Now, okay. All right, well, that little piece, here's the formula, 1/2 mv squared. Right? Now, that little piece of mass has some amount of mass. I'm going to call that dm because it's a little piece of mass. Right? Seems like a reasonable choice. We'll elaborate on that later. But the punchline is dm is just going to be density times size. It's the usual. Okay. V, don't forget we have this formula. V is omega r. Okay. Altogether then, with V being omega R. Kind of moving things around a little bit. Now take this, let's see here, we're going to take this 1/2 and pull it outside of the integral. We're going to take the omega squared here and pull that outside of the integral. That's just shuffling things around, perfectly legal. And note we end up with this expression. Now, how does this help us? The way this helps us is that structurally looks a lot like this formula. And so these are kind of two different versions of kinetic energy formula. This one is what you might call the linear kinetic energy formula, on the assumption everything's moving in a straight line. This is stuff naturally phrased in terms of things that are moving in a linear fashion. V is actual linear velocity. This is the angular version. So notice structurally, it's got a lot of the same earmarks. It's 1/2 of something times a version of velocity squared. It's kind of 1/2 size of something and then a speed in some sense squared. It's got that same sort of structure. Difference being, of course, that this is not linear velocity. It's angular velocity. And with that idea in mind, that makes us have a reasonable candidate to call that. That's not linear, kind of the linear version of mass. This is the angular analog of mass. Right? So that's why we are interested in this expression right here. This is, in an angular formulation, when something's moving at a constant angular speed, angular velocity, this thing, this expression that you can see the algebra, it just kind of shows up this way. This is the thing that plays the role kind of like mass, and it's called moment of inertia. It's very commonly represented by the capital I. And we have this formula here, integral r squared dm. So I strongly encourage you to memorize this formula, integral r squared dm. There's lots of different versions of this formula, depending on what are you rotating around? What is that distance to the axis of rotation? We're going to talk about those different versions in a moment. By the way, there's a three-dimensional version of this. This currently, you'll notice, is a double integral. It assumes we have a two-dimensional piece of mass. All we know how to do is break up two-dimensional things right now. Right, we'll get to three-dimensional stuff later, as in later today. But for the moment, this is only the two-dimensional version. But in all cases, all versions of moment of inertia, it's integral r squared dm. Interpret the integral appropriate to the context. Interpret r appropriate to the context. Interpret dm appropriate to the context. So this is the version to memorize. Is everybody on board? See what I'm saying? Please don't try to memorize all, 30 some odd variations that could possibly come from various combinations of other factors. Okay, so let's talk about what is r. So it depends on what's rotating around what. So, various cases. Let's suppose that you have a two-dimensional region. Again, that's all we really know how to break up anyway. And suppose that is rotating around the z-axis. Okay, well, it's rotating around the z-axis. That means that the distance from some little piece of that mass to the axis, yeah, little geometry problem, no big deal. Pythagorean formula, square root of x squared plus y squared. Conveniently, it's the familiar notion of r from polar coordinates. Okay. That is a peculiarity of this circumstance. Notice this other circumstance where you're rotating around the x-axis, let's say. And again, you have a region that's in the xy plane. Well, what is the formula now for the distance from a little piece of this mass over to the axis? Well, now the distance is like that, right? The distance to an axis is measured perpendicularly, and that distance is no longer square root of x squared plus y squared. That would be wrong, right? Now the formula is just absolute value of y. Okay, so etc. Right? I mean, here's other versions, a couple of quickies. Again, please don't memorize all of these formulas. for all of the various different contexts. I think I can persuade you that there's bazillions of different contexts. These 4 that I've enumerated are all just for regions in the XY plane. What about regions in the YZ plane? Or the XZ plane, right? There's just bazillions of different versions of this. So always give yourself the corresponding little geometry problem. It's not that hard of a geometry problem. Identify where is your region, right? Draw a little picture. It doesn't even have to be a good picture. It just has to be sort of in the correct plane. Right here we have a region given in the XY plane. Identify very clearly what is the axis that you're rotating around. The presumption here is that we're rotating around this axis given by that equation, x equals a. Take an arbitrary point, x comma y in your region. Draw what is the distance from that point in the region on your mass to the axis that you're rotating around, and then ask yourself a little geometry problem, what is that distance? And so here, for example, absolute value of x minus a, right? So it's going to be different for every picture. But the way you find the answers to what r is always the same game on these various different pictures. Everybody on board? Let's go with the picture. Don't memorize. Memorize this. Right. Okay. Alrighty. So here's an example. Let's find the moment of inertia. So we've got an area here. The area. Whoops. Got the area between y equals sine x, the x-axis, x between 0 and pi, right? So that's this region in here. There's our region. So we've got a certain amount of mass in that region. Okay. And I want to know what's the moment of inertia of this around the x-axis. Well, let's identify it there in the statement of the question. That's what the axis is. Let's draw that on our picture. All right, let's play the usual game. So here's an arbitrary little point, x comma y. What is the radius arm, if you will, is this distance right there. Easy geometry problem, r is y. Right? Read it straight off the picture. You could argue absolute value of y, but notice that for every one of these points in this region, y is never negative. So you don't have to write the absolute values in this case. Handy. So r is y in this situation. So our memorized formula for moment of inertia, integral r squared dm, becomes integral y squared dm. Now here I didn't give any indication of what the density is. Assume the density is 1, and therefore dm is dA, and now it becomes a nested integral. Yeah?
Since you're squaring it anyway, do we still apply the absolute values?
I just think it's kind of kosher to, it's just, there's this philosophical problem of, is it bad to write down something that's false if we know that the falsehood's going to disappear by the time we get to the end of the question, right? And the argument can be made if all you're interested, you see where I'm going with this, right? Yeah. Okay. So, this being a class about reasons and not answers, let's try to not write down stuff that's false. I would say try to make sure that everything is correct, even if it's harmlessly incorrect. Yeah. Great question, though. Anybody else? Everybody happy? Okay. Now I will point out while I'm here that there is a sad fact about multivariable calculus, is that it involves a lot of single variable calculus. Right? It doesn't go away. It's really annoying. But here's what the outside integral turns into in this case. And integral of sine cubed. Well, that's one of those annoying, Calc 2 integrals that you had to memorize, the little trick. It's a little puzzle. It's like, there's lots of different versions of this puzzle. How do you do this integral? How do you do that integral? And Calc 2 does a bunch of those games because a bunch of those games show up in very natural application scenarios such as this. So make sure you remember how to do this integral. Now in this case, the trick is, well, obviously we get rid of the 1/3, then use the Pythagorean identity. Sine squared is 1 minus cosine squared. And then notice that that's an easy integral. And this is just an easy u substitution. Now you just got to remember what the little trick is for this little annoying little integral. Okay? So reminder, Calc 2 is a prerequisite for this course. If you've already burned your Calc 2 book in a barbecue pit, after the end of last semester, see if you can find a used copy somewhere, right? Brush up, make sure that you're still good with this kind of thing, because these kinds of integrals will show up in this class. By the way, just for more discussion in that general area, we were actually specifically requested by the engineering school. Most of y'all are engineers, not all, but most of y'all are engineers. Please don't let up on the single variable calculus in your higher level classes, because we really need our students to be good at doing integrals, and this was about 10 years ago or something. And as of that time, they were complaining, hey, you're sending us students who did well in Math 353, but they can't do integrals anymore. Right? So this is not the math department imposing its will on y'all. This is a real skill that you absolutely need. Okay. All right. Very quick comment. There's this thing called radius of gyration that's mentioned in the book. I mention it here just because it's mentioned in the book. It's a physics thing. If you're curious, it's the distance from the axis of rotation such that if all of the mass were centered, if all that mass were concentrated, I should say, at that distance from the axis with the same angular rotation speed, that the resulting particle would have the same total kinetic energy. It's kind of a weird thing to want to know. But anyway, it's called the radius of gyration. There's the formula. It's not a big deal. Memorize that formula. Feel free to memorize this formula like 5 minutes before the exam. Right? It's not like it's going to come up a lot. But anyway, there it is. Oh, I forgot a parenthesis. Look at that. Sorry about that. Okay. Okay, so let's move on now to triple integrals. This is a really interesting topic for conceptual reasons. And I ask a modest question, on what application should I model this construction of a triple integral? Reasonable question, right? So what application did we model single variable integrals? Well, area under a curve. Here we go. Where do I get Riemann sums from in this form? Well, I got it by considering this question, right? Area under a curve, and coming up with a strategy for how to compute that area under a curve, and it motivates the need for this formula. And then having written down this formula, then we can argue, by the way, hey, this can also be applied to this question of how much mass is on a rod, and we can write down also an integral. In other words, also a Riemann sum. And so, but nevertheless, it all kind of stems from area under a curve question. Okay. Let's look at double integrals. What was the history of double integrals? Kind of the same thing, right? The very first application that we came up with for a double integral, was how much volume is there under a surface, specifically a graph, right? And okay, well, we use that to motivate this Riemann sum, and then we use that Riemann sum to answer this question: how much mass is there in a two-dimensional region, for example? And you get this. But anyway, the motivation, again, left to right there. Yeah. Okay. At this stage, I can turn these observations, and we can look at it from a different point of view. What's the way that you would perhaps most naturally view a single variable integral? Should you view single variable integrals as areas under graphs, or should you view that as, in your mind, conceptually, how should you think about single variable integrals? Should you think of it as an area, or should you think of it as representing a mass? I think there's the pros and cons, different advantages, disadvantages, but that's one reasonable way you could say it. Likewise here, what's the best way to think about a double integral? Should you think of it as volume under a graph surface, or should you think of it as the amount of stuff given stuff per unit area? What's the total amount of stuff? Right? And y'all will recall, because I've said it a lot, that I'm aware of the fact that y'all, students in general, I'll not make this personal, students in general tend to rely very heavily on this one. And the case that I've made up to now is don't rely exclusively on this picture. Make sure to also kind of digest this as well, and maybe not as much that one. Okay, so this is all reminders, background. So here we are, and now let's ask the next natural question: what if we bump it up one more dimension, right? What would be a reasonable way to think about a triple integral? What application in this world that we live in could we use to motivate a triple integral? And I make the case that you can't do it from this graph point of view. We run out of dimensions, right? For a single variable integral, you get here, let me write some numbers down here. For a single variable integral, you get a two-dimensional picture. For a double integral, you get a three-dimensional picture. If you want to make some sense out of a triple integral, we're going to have to draw a four-dimensional picture, right? So that's a hard no, right? Can't possibly. It doesn't make any sense. Okay. But look at how the dimensions go on the other side of the picture. For a single variable integral, the mass point of view, or the accumulation of stuff point of view, motivates a one-dimensional picture. For a double integral, the accumulation of stuff picture over here is a two-dimensional picture. A triple integral, easy analogy to extend, right? Instead of asking how mass accumulates over a one-dimensional rod or a two-dimensional sheet, we could very reasonably just ask, okay, given me a three-dimensional solid, how might I address the question of how mass adds up over that three-dimensional region? Perfectly natural sort of physics application. Right? So the big point I want to make here, and I make a huge deal out of this. I just killed 5 minutes on this problem. Right? I make a big deal out of this because so many students make the mistake of trying to understand single variable integrals from that point of view, because that's how we did it in high school, and double integrals from this point of view because it seemed most familiar to what they did in high school. Right? And they get to triple integrals, and they're trying to visualize this, but the instructor's always drawing these pictures and what's going on here, and it's really easy to get confused as to what's going on. It's a really unnatural perspective. Right? So this is yet another reason why I'm not a big fan of this point of view. I don't think you should never take that point of view, but certainly do not, make this the cornerstone of your understanding of integrals. It's really, really bad. It's a big problem. This, I contend, is a much better sort of fundamental cornerstone point of view to have on integrals. Because this is the point of view on integrals that allows you to have a chance of understanding triple integrals. Everybody on board? Yeah.
If we assume the fourth dimension is time, would it be like the volume accumulated over time?
My gosh, I don't know. There might be a point of view there. Man, I'd have to really think about it. But that's going to be I don't want my understanding of triple integrals to rely on my ability to visualize time as a fourth dimension. Right? It's a real tough choice. Yeah. But maybe. Now I will say one other thing. Not everything in this course is necessarily about stuff that you can visualize. There are certainly some situations where you will need. Well, I don't know about y'all personally, but there are plenty of situations where integrals need to be written down over domains that you cannot visualize. Again, not everything's about the three-dimensional world, right? We talked about some econ examples on the first day of class where, sometimes we got, profit example, is a function of 5 or 6 different input variables. Right? If you need to do some sort of an integral there, you're doing an integral on a 6-dimensional domain, and you can't physically visualize that, sure. Right? But you can still kind of write it down and everything. But why add fuel to the flame if you've got a 6-dimensional domain? Why do we make it worse by trying to understand an integral as a 7-dimensional picture defined over that 6-dimensional domain? Right? That's just making it harder. So anyway. Okay, we're going to draw the line here. We're not going to do any quadruple integrals in this class. Right? But let me just point out, if you did do a quadruple integral, it's just kind of the same thing as this. You've got to visualize that you've got some domain for whatever reason, variables that have some interpretation, and think about what is the purpose of your region. How would you break your region up into little subregions? And what is it that's actually, what kind of a notion of density do you have on that little region? Maybe you're adding up probabilities, for example. Yeah, right? And you can write down a Riemann sum, which is an integral. So anyway, it's been done. No big deal. Okay. All right, so with all of this having been said here, motivated by this problem, this, a.k.a. this, is our definition for a triple integral. And I've got a 3-dimensional thing. I'm going to chop up that 3-dimensional thing into pieces. On each piece, the accumulating quantity, I don't know, maybe it's mass. Well, mass is a density times a volume. Maybe I'm computing something else. Maybe I'm computing, I don't know, like a probability. Well, then there's a probability density function that I multiply by size, in this case volume. Right? But in all cases, whatever you might be computing, population, we've got a bunch of flies flying around, mosquitoes, whatever, inside of this, our mosquito net, unfortunately. And in some little region, if I know the number of mosquitoes per unit volume, multiply by volume, that gives you mosquitoes, an accumulating quantity, right? Yeah. Okay. So that's the construction, lots of applications. So forget about the graph point of view, at least, for sure, in the context of triple integrals. Just absolutely jettison the graph point of view. Think of everything in terms of, my personal favorite of these many other applications is thinking of mass, just because it's so visceral. Right? I can relate to the idea of density. I have an intuition for density. I can't see inside of a solid block of wood. I don't have that kind of X-ray vision or something. I can't geometrically visualize, but I have a sense for it. Right? And so, better than stuff like probability. I don't know, it's kind of hard to put your hands on probability. How do you see probability? That's tough. I have no intuition for probability. It's not something I can feel. Mass is something you can kind of feel. So this is where I hang my hat on triple integrals, and I encourage you to consider the same. Okay, moving along. A quick observation about densities. So there's lots of different points of views on densities. We talked about that previously. Hope you all remember. A common point of view on density is mass per unit size, right? And we talked about mass per unit length for single variable integrals. We talked about mass per unit area for double integrals. Now we're talking about mass per unit volume for triple integrals. And I'll make the observation that that's the one that's actually more familiar anyway. Mass per unit volume, right? Everyone's first understanding of density in 9th grade physical science class is mass per unit volume. So here we are again. Right? But that said, I do want to point out that densities can be interpreted in lots of different ways. What it always is, this term density should always be interpreted as some amount of some stuff, Q for quantity, right? Whatever that might be, stuff per unit size. All densities are stuff per unit size, suitable to the application. Okay. So, for example, if you're talking about mass, then we have this notion of mass density. Again, 9th grade physical science, right? Old news. If we are talking about pollution in the atmosphere, let's say, right? Well, okay, so pollution per unit, pollution, a quantity of pollution per cubic meter in the atmosphere, per cubic mile or whatever. Concentration. Right? So you should think of concentration as a sort of a density. Right? Again, with the population density, right? If you have some sort of, bacteria or, microbes or what have you that are floating around in an aquarium, let's say, in the water, and you want to talk about the population density of bacteria. Well, population density means number of bacteria per unit, per unit volume, so maybe per cubic centimeter or whatever inside that aquarium. Okay. So last observation along these lines, and this is, I can't be more precise than this at the moment, but y'all apparently all heard the rumors about Chapter 15, the vector calculus, and all the challenging ideas that are in Chapter 15. A really big point of view, a really valuable perspective from Chapter 15 is that some of those quantities that we're going to write down and do big things with can be thought of as densities. Right? And instead of being some sort of a physical stuff per unit volume, there are going to be geometric quantities that accumulate in the same way as physical quantities. So what I mean by accumulate is, so mass is an accumulating quantity. If you have an actual mass, if you have a loaf of bread, right? If you slice up the loaf of bread, the sum of the masses of the slices of bread is the same as the mass of the original loaf of bread. So mass is an accumulating quantity in that sense. Everybody see what I'm talking about? So, the word density suggests that you're talking about an accumulating quantity in this sense. There are going to be geometrically accumulating quantities that we will see in Chapter 15 whose corresponding notion of density, the amount of this geometric stuff per unit size, is going to be really, really important. Right? So anyway, this is yet another reason to rely on this point of view for triple integrals. Because this is how you're going to have to think in Chapter 15. Okay, all right, I think it's enough sales pitch. Let's go on to the actual computations. Quick flashback to double integrals. Y'all remember how double integrals worked, right? We wrote down double integrals. It's a Riemann sum, and we don't know how to compute those. What's the point in writing down a mathematical expression if you can't compute it? Right? And so we were very pleased to find that we could rewrite the double integral as an iterated integral. Right? Everybody remember that? Okay. And I gave a geometric argument to motivate why this is reasonably expected. Now, let's be careful, though. This outer integral, the bounds for that outer integral come from looking at the entire domain, and you look at slices as you slice perpendicular to the x-axis, and the bounds x1 and x2 come from, as you slice up the entire domain, what's the starting value of x, what's the ending value of x. Yeah? I've done 1 million of those, so, okay. On the other hand, for the inside integral, we don't look over the entire domain. We fix a single value of that outside variable. We fix a value of x. And then, for that given value of x, and only on that x slice, on that value of x, you look at the range of values of y. So y1 depends on x, y2 depends on x, as what's the range of values of y on that, God, I said that backwards. For a given value of x, y1, actually I think I did say it right, y1 and y2 depend on x because it's only on that x slice that you want to know what's the range of values of y. So said geometrically, you look at the x slice, and it's only on that x slice that you want to know the range of values of y. Right? You don't want to know the range of values of y on the entire domain. You're not on the entire domain, you're just on that x slice. Everybody remember this? Big point here, right? Okay. So the motivation that I gave for this, back when we were doing double integrals, involved drawing that graph picture, right, that I keep dismissing and then using. It has its moments of usefulness. But reminder, I can't draw the graph picture for triple integrals. So I'm not going to be able to justify this formula. here, this point of view. But I think it's highly plausible by analogy. So here's the idea. You have a triple integral. The outside integral, the range of values comes from looking at the entire domain. We're going to look at the entire domain and ask what's the smallest value of x, what's the largest value of x. Having done that, we're going to fix a value of x. And we're going to look on that x slice, and only on that x slice. On that x slice, we're going to then look at the resulting range of values of y. Now, just like with a double integral, that means that the y bounds are going to depend on x. Different value of x, different x slice, different range of values of y. Yeah? Okay. And then repeat. To get the bounds on the inside integral, not only do we keep x fixed, but then we're going to then fix a value of y. We're going to look then at a y slice of the x slice. We're going to draw some pictures in just a moment. We fix a value of y. We're looking at a y slice of our x slice, and then on that y slice of our x slice, we look at the range of values of z. Yeah?
Are we going to go over like how you determine which order is best?
Yeah, a little bit. Yeah, it's another thing I am going to talk about. Yeah, that's right. And it's a hard question. Yeah. Okay, but let's for the moment I just want to get the slicing process discussed here. By the way, a terminological observation. How do you refer to these integrals? Just like with double integrals, I strongly advise against using first, second, third, right? Because the slicing is first, second, third, but the evaluation is first, second, third. It's the opposite order. So it's super ambiguous if you say first, second, third. But I think calling this one outside is unambiguous. I think calling this one, inside is pretty unambiguous. This one, a little bit awkward, but notice you could call it second, and there's no ambiguity. It's second either way. Take advantage of the wins when you get them, right? So you could call that second. You can also call it middle. Anyway, but be careful. Don't be too sloppy in your terminology and your way of thinking about these things. So anyway, heads up on the terminology. Okay, so let's do a slicing process. Let's see what this actually looks like. How do we find the range of values of x? Well, I'm making cross sections perpendicular to the x-axis. I'm slicing through perpendicular to the x-axis. And those x slices start way off on the back end of this little kidney bean to give me my x1. They end way here at the front to give me my x2. Looking over the entire domain, in other words, what's the range of values of x? Okay, so that's exactly sort of as expected. Okay, now we fix a value of x. So that x is no longer going to move. Well, I mean, it's going to move between x1 and x2, but we're going to fix a value of x for the moment to see what happens to the more inside integrals. So for that value of x, so now I'm looking exclusively on this cross section. Don't care about that stuff anymore. We'll get to those for other values of x. For this value of x, we're only... Sorry, missed the thing here. We're only on this x slice. Now, on that x slice, I want to know the range of values of y. So I'm going to do y slices of my x slice. Okay, so I've got to imagine now slices perpendicular to the y-axis of this green slice perpendicular to the x-axis. It's a slice of a slice. Yeah? Everybody on board? And I appeal to your geometric intuition. That's going to give me a bunch of little sort of line segment kind of slices like that. It's just, when you slice up the solid, you get an area. When you slice up that area, you get a little twig. Okay? All right? And so you ask then, what's the range of values of y? Well, again, on this x slice, there's the first value of y. That gives you your y1. There's your last value of y. That gives you your y2. Everybody happy? Okay. Okay, then, as usual, we fix a value of y. So for some value of y, let's fix that y. Keep in mind we've already, I guess I'd better zoom in one notch. This is getting small. We've already fixed x. That's of course not going to change. Now we're going to look only on that fixed value of y on that fixed value of x. So we're going to restrict our attention just to this one little twig, and on that twig we can ask what is the range of values of z. Now I don't care about the z coordinates over there and there. I don't care about the z coordinate here or there. I'm only interested in the z coordinates on this thing, and there's the lowest value of z, there's the highest value of z on that y slice of that x slice, right? And that gives me my z bounds, which of course depend on x and which of course depend on y, because we're only looking on that specific y slice and that specific x slice. Okay, so that's the process. This is what it looks like geometrically. I think the best way to get a handle on how this looks in practice is to let's get our hands dirty and actually do some. So I've got a bunch of examples to go here. To your question, yeah, you've got 6 different ways that you can slice, right? There's 3 different choices that you have for the outside differential. Having chosen one, you still have 2 different choices for how to order the inside differentials, right? So that's 6 options. Sometimes it doesn't matter. Sometimes it does. I'm going to make observations about this as we go along. So, yeah, it's a hard question. Okay, but first, let's just see how the slicing process goes. So I'm going to take a really, really easy starting example bounded by these 4, what's the matter with me? X equals 0, silly. Y equals 0, Z equals 0, and X plus Y plus Z equals 1, and I think you can see that gives you a solid that's just this tetrahedron. Everybody happy with that? Okay. So on this solid, let's assume that we do the slicing in this order. So X slicing on the outside. Let's just get some bounds written down on this one. Okay, so what are the X bounds? Where does X start? Where does X end? Here's what my X slices look like. Whoops, come on. Right, as I slice perpendicular to the x-axis, that's what the slices look like. You might say these are the starting slice and the ending slice. Recall, now, my preferred perspective on this is think in terms of bounds come from points. Points are on shapes. Shapes have equations. Write down those equations. Then solve for what you're interested in. Right? It's just like with double integrals. It's just more. Okay, so here we go. Let's talk about that point. Well, it's pretty, at that point that you might say defines this first slice. Pretty easy to see that x is 0, so sometimes the fish just jump right in the boat. Right? So that's very convenient. Okay, but what about this point? What can I say about that point? Where is that x bound going to come from? Well, you got to think about the shapes. That point is on that plane, right? It's on, let's see here, it is on this plane. It's on this plane. Yeah? By the way, can you imagine possibly trying to do this without the picture? It'd be really hard. You've got to be able to see exactly which planes are defining the point that you're interested in. And I can't do this in my head. and I don't think anyone can do this in their head reliably and in all circumstances. So draw the picture. By the way, another observation on pictures. Notice that I've made myself a pretty big picture here. Right? That took up most of the width of the page. Give yourself plenty of space. Another reminder, you're welcome to come into the exam with a straight edge if you want to make sure that you can draw better pictures. Right? Feel free. Do whatever you got to do to make sure that you have a really decent picture. Okay, so we have those equations. So here are the three equations that define the problem that I'm interested in to give me the bound that's associated to that point. I am looking for the x coordinate. Right? So I need to solve for x. Note this is easy because that y is 0, that z is 0, and therefore it's pretty easy to see that that x bound is 1, and thus the 1. Everybody see what happened? Now again, if you want to make the case that, well, in this case, come on, I can just kind of see it. Okay, maybe in this really easy case. Maybe, right? But not in all cases. So stick to the process. It will pay off. Okay, so let's talk now about the y bounds. What's the range of values of y? Okay, well, let's see here. The range of values of y. Well, we're going to stick to a particular x value. There's a fixed value of x. We are now no longer interested in what's going on anywhere else. Just that one x slice. Oh, come on. On that x slice, what do y slices look like? Y slices look like that, as you slice perpendicular to the y-axis. Yeah? Okay. All right, so where's the first and last slices? So again, on this x slice, the first y slice, I'm going to say that point. The last y slice, I'm going to say that point. This first point, well, it's pretty clear. Again, get lucky sometimes. That one's pretty clearly y equals 0. It's in the plane y equals 0. Easy to solve for y. Okay. But what about this point? What do I know about that point? Well, again, you gotta think it through. I mean, look at the picture, think about the geometry, and write down the equations. You've got to have a good picture for this. So that point that I'm interested in, that defines my y bound, it's on that plane. It's on this plane. And, oh yeah, I've already picked x, right? X has been chosen. It's on this slice. So x is whatever it is. Again, go through and solve for what you're interested in. You're trying to find the value of y there. Solve for that y, and you'll notice 1 minus x. So that's this y bound. Notice that it is a function of x. That's okay. It's supposed to be a function of x because it depends on the now fixed value of x that defines that slice, just as it should be. Okay. Very quickly for this, the last, the inside. Okay, now looking at this, okay, there's a y slice of our x slice, right? So now x is fixed, y is fixed, right? We're fixed both of these. Z starts there. It's pretty clear z equals 0. It's in the plane z equals 0. So that's easy. But this point, what do I know about that point? Well, okay, that point's on this plane. And I know x and I know y. Solve for z. And I get that my upper z bound is that. Everybody on board? Ever see the process? Many more non-trivial, geometrically challenging examples will come next time, which will be after fall break. So see y'all later. Have a great break. Oh, and I have homeworks to return.